In this video, we're going to be talking about CCC 2010 S4 Animal Farm. And in this problem, essentially what they're asking us is to find the minimal cost that will allow all animals to gather in one pen or outside all of the pens. So the way this question works is that we're given an input. So we're given that there are 4 pens. So we can see that there's 1, 2, 3, and 4. And we should notice that each pen is represented by some corners and an edge cost. So we can see here that 1 and 2, so corners 1 and 2, are dividing, so they're connected via an edge of 7 here. So we can see that 1, 2 connected with an edge of 7. We can see that 2 and 3 are connected via an edge of 4. So that's right here. And then 3 and 1, because of the way the input was given, it's a cyclical order. So it's going to go 1, 2, 2, 3, and then 3 to 1. So 3 and 1. And the cost of that edge is going to be 6. So you can see 3, 1 or 1, 6 or 1, 3 is going to have an edge of 6. And the exact same thing happens for all other edges. Now, if the edge is sharing 2 pens right here, we can see that 1 and 2 is still going to have a cost of 7. So it's going to remain the same. Okay, so now that we know how the pens are, or how each of the pens are labeled or defined as, let's look at exactly why the answer is 10 in this case. So here I have the graph drawn out already. And what we're going to do is we're going to look at exactly how the answer is 10. So one possible solution might be to remove this edge right here. So we're going to get an answer of 2 plus, and let's say we're going to remove this edge here. So we're going to have 4. And now what you should notice is that this edge right here is connected to this edge right here, or sorry, this pen. And what you should notice is that this whole pen becomes one entire pen because they're no longer separated by a fence. And the exact same thing happens with this pen right here. So now all 3 of these pens become 1, right? And finally, what we're going to do is we're going to remove this pen, for example, or this fence, and we're going to get a sum of 4. Now that we see that, we can see that this entire pen here, this entire pen, and this entire pen are all 1, and now all the animals can meet up in one single position, or one single pen. And so here you can see 2 plus 4 plus 4 gives an answer of 10. So that's one of the solutions to this specific sample input, giving us a total answer of 10. Okay, so now you might be looking at this and you might be saying, okay, this is kind of an algorithm, this seems like a problem that I kind of already know. And the way you might have seen me doing it is I took the smallest edge, right? The smallest fence cost first. So I'm going to actually rewrite that equals to 10 and erase all of this. What you should have noticed is that I was taking them in order of increasing pen costs, right? A fence cost, right? So I'm going 2, 4, 4. And does this seem like an algorithm that we kind of already know? Well, yes, kind of. So we might be looking at this and we might be thinking, all right, this might have something to do with some minimal cost algorithm, and more specifically, an algorithm that we already know called minimum spanning tree. Minimum spanning tree. Okay, so now you might be wondering, how do I run minimum spanning tree on this? And initially a lot of people think that for this question, the corners are the nodes. And that's one of the common misconceptions for this question. We're not trying to connect all the nodes together. In fact, we're trying to connect the pens together. And so if we're trying to connect all the pens together, what we can do is we can represent each of the pens as nodes themselves. So if I were to construct the graph or some kind of data structure for this sample input right here, we might say that this is node 1, right? And let me use a different color, a more darker one. So this might be node 1, this might be node 2, this might be node 3, and this might be node 4. Okay, so now you can see that these are the nodes because we're trying to connect them all. And what you can see is that the edges or the fence costs dividing the pens is actually the cost of the edges. So you can see here, it's going to have a cost of 7, a cost of 2, a cost of 4, a cost of 7 here, and then finally a cost of 4. And so if I erase all the sample input stuff, so now it's going to look something like this. And now, like I said earlier, we can run a simple minimum spanning tree algorithm on this. What we're going to do is first sort the edges, and then we're going to just greedily take the edges with a smaller cost as long as they don't form a cycle, right? Because we want a tree, and with a tree, one of the properties is that it doesn't form a cycle. And so by doing that, we can see, take this edge here, right? Take this edge here, or that edge, it really doesn't matter. So let's take this one. So 4. And then finally take this one, giving us a total cost of 10. Okay, so there's that. Now, the question is, how do we actually, construct this graph, right? Because running the minimum spanning tree algorithm is kind of the easy part of this entire question. Although not a very standard algorithm, the prerequisite for this question would be to know minimum spanning tree. Okay, so let's bring the graph back. Now, like I said earlier, or just said, running the minimum spanning tree is the easy part of this problem. Now, one of the things that you might want to watch out for is that in the problem specifically, they say that we can also meet outside of the pen. So we're going to also run minimum spanning tree or the minimum spanning tree algorithm not only with the nodes or the pens as the nodes, we're also going to have the outside as a node as well. And we can mark that as node 0, for example. Okay. So what we're going to do is we're actually going to run Kruskal's or Prem's algorithm. I guess in this question, we're going to use Kruskal's. We're going to run Kruskal's twice. So we're going to do it once when the animals can only meet inside the pens, like inside the entire encapsulated area, right? They can only meet within these bounds. And then a second time we're going to do this is we're going to also allow them to meet outside if that is an optimal solution. And the reason we do this is that because the way minimum spanning tree algorithms work with a kind of greedy approach, we might be cutting an edge out here that isn't an optimal solution. Especially in this example, we can see that if we're trying to meet outside, it's not an optimal solution actually, right? Okay. So now for this question, we just really need to construct this graph. And let's look at exactly how we might construct this graph. So I'm going to erase a few of these things here, and we're going to look at exactly how we're going to construct this graph. Okay, so we know from the problem that the question is defined, or each of these pens is defined as 2 corners, right? A few corners and the cost of the corners, right? Okay, so we know that we have, for example, this is pen 1. And the reason we call this pen 1 is because it's the first in the input, right? This would be pen 1, so we would just call it pen 1 because of the order of the input. Okay, so we can call this pen 1. And what we notice is that each of the pens, or each of the connections even around each pen, is defined by corner 1. So I'm going to call it corner 1. And it's connected by some edge, right? So maybe like that. It has some edge here. And then we have corner 2. Okay. And let me redraw that. There we go. And so what we're going to do, right, since we have each of the edges, or each of the input consists of a corner 1, corner 2, and then an edge, what we're going to actually do is we're going to store these in a 2D array of array list pairs. So that seems a little abstract right now, but it's going to make much more sense when we look at it exactly how this is going to work. So like I said, we're going to need a 2D array list, or sorry, 2D array of array list pairs. So how does this work? Okay, so this is how exactly it will work, and maybe I'll write out the declaration for it first. So what it's going to look like, and I'll write this in black, is it's going to be array list. And the type of the array list is going to be of type pair. And we're going to look exactly what the pair will store. So we have an array list, and it's going to be in some kind of 2D array of size and by n. Okay. And n is not the number of nodes, sorry, in this case. It would just be the number of total corners. So maybe this would be size 1000 by 1000. Okay. So that's what it's going to look like, right? And essentially what's going to happen is for every dual ij, so the name of my 2D array is going to be called dual. And what I'm going to say is for every dual ij, so dual ij, what it is it's going to store an array list. So it's going to store a list of pairs. And what it is it's going to be a list of, so for every ij, so this is going to be corner 1, so corner I, for example, and this is corner j, and let me use another color. So let's say we had corner I, and let's use this one here, corner I and corner j. So let me erase this, corner I and corner j. Okay, so we have corner I and corner j, and essentially what it's going to do is it's going to be a list of pens that it's separating right now. So we can see that this ij right here, 1 and 2, so it would be dual 1, 2, is going to store what are the pens that it's separating. So it's going to store a list of pens the fence is separating. Okay. So hopefully that makes sense. So we're going to say dual ij is going to store, for example, 1 and 2. But what does the pair mean? So obviously we can store these as integers, but what I also want to store is the cost of the fence as well. So it's not only going to store the list of pens the fence is separating, it's also going to store the cost of the edge. Okay. So once again, dual ij represents an array list of pen cost pairs divided by the edge formed by corners I and j. Okay. So if that makes sense, then what you should notice, and I will erase this and make it a little simpler. So I'm going to say a list of pen, like for example, k, and cost k as well. Right? It's going to be a list of which pens are it separating and what is the cost of the edge. Okay. And so what you should notice is that once dual ij has a list of 2 pairs, right? It has a list of 2, so that means basically dual ij.size, and maybe I'll rewrite it down here or up here. Let's say that once dual ij, and we'll use the color coding, dual I j dot size, right? If the size of the array list at dual ij is equal to 2, then I know that it's separating 2 pens. And in this case, we know that a fence can only separate at most 2 pens, right? And so therefore, if the size of dual ij is equal to 2, we know that it's completely separating 2 fences now. So we know that it's separating 1 and 2. Okay. So then what we're going to do is basically we're just going to add to our edge list. And because we're using Kruskal's algorithm is just a little easier using an edge list. And so when dual ij.size is equal to 2, add to our edge list. And what exactly are we going to add to our edge list? Well, we know that an edge list is defined by node 1, right? Node 2, and then a weight. And I don't have to include these i's like that. So it's going to represent u, v, and w, right? So what are we going to do, right? How do we extract this information? Well, it's very simple, right? All we have to do is say u is the first node. So what is the first pen that I and j are separating? How do we extract that information? Well, all we have to say is dual, and I'll leave some room for I and j here, ij. And we know that it's an array list, so we're going to say dot get 0, right? Because it's an array list of at most 2 elements. And what we're going to say is in that pair, we can say, for example, dot first or dot pen even. And that's going to be u. Now, how do we extract v? Well, we can do the exact same thing. So I'm going to write it down here. And we're going to say v is equal to dual. Leave some room for I and j. Dot get 1, right? Because dual ij only gets or only stores at most 2 pens. And so what we do is dot get 1 dot pen. Okay, now how do we get this weight here? Well, the final weight, and I'll erase these and just put them together like so. Make that a bit smaller. And the way we're just going to get w is very simple. We just have to do the exact same thing. We just say dual ij. And in this case, it doesn't matter which one you use. You can use 0 or 1, but we know that that dual ij is going to share the exact same cost of the pen, right? And so we can just say dot get 1 or 0, really doesn't matter, dot cost. Okay, and then finally, once we're done that, we can just run Kruskal's algorithm once we're done creating the entire edge list. Okay, now one of the problems with doing this is that we're only running Kruskals once, right? Like I said earlier, we need to also consider the outside as a pen as well. And so that can be easily done. If we understand the construction of dual ij and the edge list, all we have to do is really find, right? If we're trying to say that node 0 is the outside, then all we have to do is look at which dual ij's, right, have a size of 1, right? So if this was my ij right here, so 3 and 8. So let's look. I and j is here. Well, if the size is equal to 1, right? If dual ij dot get size is equal to 1, that means it's only connecting or neighboring this edge right here. This fence is only neighboring 1 pen. And so that means it's neighboring the outside as well, right? And so if the size of dual ij is equal to 1, that means we can start connecting that edge to our inner edge. So let's say this was 4, this would have an edge of 7. The exact same thing might happen here with an edge of 6, here with an edge of 6 as well, and so on. And then we're going to run Kruskals algorithm one more time, right? Sort the edge list by the increasing weights. And then all we have to do is run Kruskals algorithm, compare the two answers. So let's say we had two answers, so answer 1 and answer 2. All we have to do is take the minimum of both of them. Okay, so if that makes sense, let's code it up. Okay, so now that we know how the algorithm is going to work, we can start writing it. So once again, we're going to be using Kruskals algorithm for this. And so with Kruskals algorithm, we're going to need a few data structures that are very important. So the first data structure that we're going to need, or the first two, I guess, is that pair, the parent, and the rank. So parent is just going to store what is the lead or the parent of the current set, right? If you don't know how Kruskals algorithm works, I suggest watching the video on Kruskals and prims, and then you'll get a better understanding of how this question will work. So we're going to have two arrays, which are the parent array and the rank array. The parent array stores what is the leader of the current set, and the rank is just what is the height or what is the size of the current set. And just because of the weighted heuristic, we want to add the smaller set to the bigger set. Okay. So next what we're going to do is we're just going to create a few methods for Kruskals algorithm, which uses a disjoint set data structure. So parent of n is equal to n, and the rank of n is equal to 1. Then here, we're going to create our find method. And for our find method, we're going to add some path compression. In this case, we don't really need to recalculate our path. And so what we can do is just use path compression to make it a little faster. So parent of n is equal to n, return n. And otherwise, the parent of n is equal to the find of the parent of n. Okay. Then what we're going to need is just that union method. So in the union method, we're going to actually make it a Boolean. And the reason we're going to make it a Boolean is simply because we just want to return true or false based on whether or not we successfully combine the two sets. So true if they combine successfully, and false if they didn't. So we're going to say union int A and int B. A is equal to the find of A. B is equal to the find of B. So we're going to make them the parent of their own sets. Then if A does not equal to B, well, if A doesn't equal to B, that means we have to successfully merge them, right? So it's going to return true automatically. And otherwise, we're going to return false because that means they're in the same set. Okay, so here what we're going to do is we're going to merge the smaller set to the bigger set. So if rank of A is greater than rank of B, the parent of B is equal to A, right? A is bigger than B, so make the parent of B equal to A. Otherwise, we can say whether or not they're the same. Well, if they're the same, what we have to do is just say the rank of B increases as well, since we're making A combined to B in this case. So parent of A is equal to B. Okay, so there's that. Now what we're going to do is we're just going to start taking in some input. So what we're going to do first is we're going to take an input for our integer n. And let me scroll down a bit so you can see all of it. And what we're going to do is we're going to initialize each of our arrays. So parent is equal to new int of size n plus 5, and the same thing for rank. Okay. Then what we're going to do is we're going to create a few more data structures. So the little data structures that we're going to need are, number one, we're going to need that 2D array of array list pairs. So we're going to say static array list, right, of pairs, right? And that's going to be our data type of our 2D array. And then this is the name of our 2D array. The next thing we're going to also need is an edge list for our Kruskals algorithm. So it's going to be of type array list, right? Like that. And it's going to be storing edges. So we're going to call this edges1. So edges1 is going to be if we consider the animals to meet inside the pens, and edges2 is going to be considering if we use the outside as a pen as well. Okay, so we're going to need to make a pair and an edge custom class. And that's very simple. We just say pair, int pen, and cost. Create the constructor for them. So this dot pen is equal to pen, and this dot cost is equal to cost. The exact same thing for the edge. So edge, but this time, because we need to sort the edges, we're actually going to implement comparable. And essentially, this will allow us to sort the edges by whatever we want to sort it by. So create the constructor. And then we need to override the compare_to method to allow us to sort however we want. So edge other, and we're going to return this .w minus other.w. And that will allow us to sort in ascending order. Okay, so now we can work back into our main method. And so we're going to go all the way down. And we're going to initialize those as well. So we're just going to say dual is equal to new array list of size 1005 by 1005, because we have at most 1000 corners. Then edges1 is equal to new array list, and the exact same thing for edges2. Now, one of the things that we have to do is, because an array list is an object, and since we're storing a 2D array of them, we need to initialize each of them to be able to use them. So we're going to loop through the 2D array, like so. Oops. And we're just going to initialize each of the array lists at dual ij. Okay. So the next thing we also need to do is actually we need to initialize each of the sets. We need to make the sets for each of the pens, and that can be easily done using a for loop. So we can just say make set I. And that make set method was just saying the parent of n is equal to n, and the rank of n is equal to 1. Okay, so let's start taking in that input. So for each of the pens, so we loop from 1 to n, we're going to take in the number of edges or the number of corners around the ith pen. And what we're going to do is we're going to store an array list of them. So we're going to, or sorry, an array of them. So we're going to store all the corners of size e and the cost of each of the corner pairs. So costs is equal to new int of size e. What we're going to do is we're just going to first take an input for them, and we're going to process them later. So we're going to say corners j is equal to read int, and the exact same thing for the costs. So costs j is equal to read int. Okay, from there, let's actually start converting our, weird kind of array or kind of corners, costs, all that into an edge list. We want to convert the input into an edge list now. So what we're going to do is first, we know that it's like cyclical. So we know that it's like kind of weird. The first two, the second two, the third two, and then the last and the first one, it's kind of weird. But essentially what we're going to do is we're going to first loop through the first e minus 1 numbers. We're going to first loop through the e minus 1, and then the last one and the first one we're going to deal later. So we're going to say int corner1 is equal to corners j. We're going to say corner2 is equal to corners j plus 1. And the cost of the corner edge, like the cost of the fence, is just going to be costs j. Cool. So what we're going to do from there is we're going to say dual corner1, corner2, dot add, because it's storing an array list of pairs, a new pair of I and the cost of the edge, right? Remember, dual ij is storing a list of pens that the current fence is separating. And we're going to do the exact same thing the other way around, just because the input is not guaranteed to be the same every time. Okay. So now what we're going to do is we're going to say if dual corner 1, corner 2 dot size is equal to 2, meaning that fence, that corner fence, is separating 2 pens in the input. So we know so far that it's separating 2. Then what we're going to do is we're going to say pair n1. So essentially what pair n1 is saying is this is the node 1. This is node 1, which is fence 1, or pen 1, sorry, is equal to dual corner 1, corner 2 dot get 0. So this is the first pen that it's separating. And we're going to do the exact same thing with dual n2. So it's going to be corner 1, corner 2 dot get 1. So it's separating 2 pens, and we're going to retrieve those 2 pens. And essentially what we're going to do is say edges 1 dot add new edge. And what is the first pen that we're separating? Well, that's just going to be n1 dot pen. And what is the second pen that is separating? Well, that's just n2 dot pen. And then what is the cost? Well, that's just going to be cost here. Okay. From there, we're going to say the exact same thing for edges 2. n1 dot pen, n2 dot pen, and then the cost of the edge. Okay. So now that we've dealt with the first e-1 numbers or corners, let's work with the last and the first one. So that's pretty easy to do. We just say corner 1, or int corner 1, is equal to corners e-1. So that's the last one. Corner 2 is equal to the first one. And then the cost of the fence is just costs e-1. Okay. Let me scroll down a bit so you can see. And then what we're going to do is we're just say dual corner 1, corner 2 dot add new pair I and then cost. So we are just doing the exact same thing we've done up there. Dual corner 2, corner 1 dot add new pair I and cost. And then finally what we're going to do is check if the size of dual ij, or dual corner 1, corner 2, is equal to 2. We're going to extract what are the 2 pens that it's separating. So we're kind of just copy pasting it almost. And then we're just adding the edges, or adding the information to our edge list. n1.pen, n2.pen, and then the cost of the edge. Same thing for edges 2. And remember, edges 2 is going to be the one where we consider the outside as well. Okay, so there we go. Now that we've successfully created our edge list of all from the input, what we're going to do is we're just going to write collections. We're going to start running our Kruskals algorithm. And the first step to Kruskals algorithm is to sort the edges. And what we're going to do is we're going to create 2 variables. One is for the answer when we consider the inside. One is for the outside. So int answer not outside is equal to 0. And then answer is outside is equal to 0. Now, the one where we consider outside isn't always going to have an answer where we consider the outside. It's just it may use the outside or not. So what we're going to do, classic Kruskals algorithm, for each edge in edges 1, we're going to say int u is equal to e.u, v is equal to e.v, and w is equal to e.w. So extract the information first. And then if union uv, so if we successfully combine the 2 sets, answer not outside plus equals w, and there we go. So now we've successfully retrieved our answer for when we run Kruskals when we only consider the inside. Then we're going to do the exact same thing, but this time we want to add some more edges to our second edge. sort to our edges 2. And those edges are going to be the ones where we consider the outside. And like I said earlier, the outside is considered to be the outside if the fence if any fence that's corner IJ, right, is connecting a fence that only is neighboring one pen, that means it's also connecting to the outside. So maybe I'll show you guys here once again. We can see here that corner IJ here, this one right here, is only neighboring one pen. And so that means we know that it's also neighboring the outside, right? So this is the outside here. Okay. So what we're going to do is we're going to loop through for every single IJ. If it's connecting the outside, right, that means the size of dual IJ is only equal to 1. So if dual IJ dot size is equal to 1, that means we know that it's neighboring the outside. So pair n1 is equal to dual IJ dot get 0, since it's only neighboring 1. What we're going to do is we're add edges 2 dot add new edge. And the edge that we're going to add is what is the first node that it's connecting. So the first node that it's connecting is the outside. So we're going to call that 0. And then what is the index of the node that it's connecting in the inside? Well, that's just going to be n1.pen. And then finally, what is the cost of the edge? Well, that's just going to be n1.cost. Finally, now that we've added it all, we want to actually reset our all of our disjoint sets. So what we're going to do actually is we're going to say for int I from 1 to n, we're going to remake the sets. We're going to reset the disjoint set and then run Kruskals one more time. So collections.sort edges 2, and then for each edge in edges 2, extract the information, e.u, v is equal to e.v, w is equal to e.w, and if we're able to successfully combine them together, so let me scroll down a bit, if union uv is equal to true, then that means we successfully combine them together, and so we can say answer is outside plus equals w. Okay, final piece of code. We just need to output the minimum between either using the inside or the outside. So math.min between answer not outside and answer is inside, or is outside, sorry. And that's pretty much it. So here I already have the sample input and the expected output, and let's run it. Oh, there's some bugs for each edge E. Okay, so let's see where we are going wrong with this. Oh, okay. So sorry, so all of this should be outside of this for loop. So this for loop only encapsulated the construction, right? And now all of this should be so this was the construction of our edge list, and then here we're just running Kruskals algorithm normally. So now let's run it, and we can see that we get all correct. Great. So now let's submit this code to see whether or not it works. And we can see, oh, all right. Seems like it's working fine. Final stretch possibly. And we can see that it gets all correct. Awesome. So here in this video, you learned how to do CCC 2010 S4 Animal Farm.